Right, the audience is filing in. We'll begin shortly though, Doctors Palmer and Shukla. So just a little bit. All right, Doctors Palmer and Shukla, if you're good, we'll begin officially.
Okay.
All righty. Well, hello and welcome everyone to AMS Weatherband's latest webinar, The Primacy of Doubt and the Science of Uncertainty, with Dr. Tim Palmer and moderated by Dr. Jagadish Shukla. Now, before we begin, folks, I would like to address some of the ground rules for our webinar today. There's just a couple, so no worries. If you have any questions during the webinar, please put them in the Q&A. If you look at the bottom of your Zoom screen, to the left of the chat, you'll see a Q&A button. Any questions that you have for Dr. Palmer or Dr. Shukla, please put them in there. That's where we'll concentrate all the questions. So we're pretty much going to not even glance at chat. We just want all the questions centered in one place so that it's easy for our guests to look at them and address them. And then we will also have some specific time for questions from the audience after the presentation. So first, I would like to introduce today's presenter. Thank you, Dr. Palmer, for joining us today. Dr. Palmer is a Royal Society Research Professor at the University of Oxford, Division Head at ECMWF, winner of the Charney and Rosby Gold Medals of the AMS and Honorary Fellow of the AMS, past President of the Royal Meteorological Society, International Member of the U.S. National Academy of Sciences. And our moderator is Dr. Jagadish Shukla. Dr. Shukla is a professor at George Mason University with a background in weather and climate predictability, including the concept of predictability in the midst of chaos. He has received multiple awards, including the Walker Gold Medal, NASA's Exceptional Scientific Achievement Medal, and the International Meteorological Prize. Dr. Shukla is a member of the Indian Prime Minister's Council on Climate Change and founded Gandhi College for Rural Education in India. So, Drs. Palmer and Shukla, the floor is yours.
Thank you.
Thank you.
Okay, Dr. Palmer, Professor Palmer.
Tim.
I can start. Tim. Okay, so from now on, Tim. So, I mean, you have an extraordinary background, you know, PhD in physics, and came close to working as a postdoc for Stephen Hawking. But then you chose UK Met Office, and then now, of course, you're after European Center back to Oxford. And so can you just tell us a little bit about how did you get interested in the field of weather and climate and this transition from quantum physics to UK Met Office?
Yeah, it was in fact a very chaotic and unpredictable trajectory. I'm a little bit embarrassed to say, you know, I read people, you know, famous meteorologists who talk about their lives, and they say, you know, I was fascinated by weather as a child. And I have to confess, I wasn't in the slightest fascinated by weather as a child. In fact, my kind of passion was looking at stars and being an amateur astronomer. And living in England, the chances are much higher that a particular night will be cloudy rather than, you know, than clear. So when there was a particular, you know, thing to look at the sky, the high probability is that you wouldn't be able to see it because of the clouds. So I used to curse the weather rather than be fascinated by it. You know, it never occurred to me at the time that I would have a career in that area. And I went on to do, as you say, well, I did my undergraduate degree in mathematics and physics, and then a PhD essentially in general relativity theory. I got, you know, involved in black holes, and it was kind of an exciting time. It was when Stephen Hawking proved that black holes can evaporate, and, you know, it was kind of an exciting time to be. But I did kind of and I had the opportunity to continue with that work, but I kind of felt at the end of my PhD, I just felt somehow that I needed to do something that was a little bit more relevant to society. And it was really just a chance meeting with another meteorologist, quite a senior one, Raymond Hyde, who convinced me that this would be a good field to go into. And I applied to the Met Office. And at the time, the Director General of the Met Office, a chap called John Mason, had a pretty liberal kind of perspective. He just wanted to take people who had a good knowledge of physics and mathematics. He wasn't too bothered about whether they knew anything about weather. And, and so I got offered a job, and sort of that started my career in meteorology.
Okay, well, wonderful. By the way, as you all know already, that Tim has written a book, The Primacy of Doubt, From Quantum Physics to Climate Change, How the Science of Uncertainty Can Help Us Understand Our Chaotic World. Tim, do you happen to have a copy of the book? Could you just show us?
Well, I have a copy of the book here, as it happens.
Okay.
This is actually the cover that is published by Oxford University Press in the UK. In the US, the publisher is Basic Books, and they've chosen a slightly different cover, but the content is the same.
I have seen that. That has no color trajectories of the Lorentz attractor.
It's a kind of an abstract thing, yeah.
Anyway, can you just tell us a little bit about, what is the scope of this book? And what are the kind of topics you have tried to cover? Because it will be good to hear from you sort of your own description for just a few minutes of the scope of this book, and how did you come about writing it?
Well, it's a little bit like my career. It's a little bit haphazard, and it's not like I had a clear path. When I first started thinking about the book, to be honest, I started thinking it would be fun to try to write a popular science book. I mean, that was the first thought I had. And it was sort of COVID and all the lockdowns over COVID that really said, well, if I'm going to do it, I better do it now. And I wanted to write something that was, I've always had a broad interest in science. As we said, my PhD work was in kind of fundamental physics, but a lot of my more recent work has been in quite applied areas. But even in the applied side, the ideas behind chaos theory are quite fundamental and basic. So I kind of wanted to write a book which tried to combine, pure science and applied science, possibly with the idea that an aspiring young scientist would realize that you can jump from one to the other. You don't have to kind of brand yourself as well. I feel very actually strongly that we don't move around in our fields nearly enough. We get siloized too easily. So this is a book which attempts to bring together lots of different fields. I mean, I suspect not only is this the only book which tackles climate change and the fundamentals of quantum mechanics, I suspect it will be for the next few hundred years as well. So really it was it's kind of a challenge to myself. Could I write such a book? Could I combine a broad area? I realized that the topic of uncertainty was quite a kind of a unifying theme. So the title, The Primacy of Doubt, which actually comes from a biography of Richard Feynman, the physicist, kind of captures this notion of uncertainty and elevating the notion of uncertainty, not to just something that you think about after you've done everything else, but, as a really primal issue. And so I discussed that from a number of different fields, including, of course, weather and climate. But yeah, so it was a kind of a challenge, and COVID gave me the opportunity to do it.
No, it is quite fascinating that you cover all the way from weather and climate, which many of us are interested in American Meteorological Society, but also you do economics, the risk management, role of noise in many things, including human brain, and you haven't touched on God and philosophy. And so obviously, I'm not going to sort of cover all of these, okay? But we will come to these one after the other. But before we come to the sort of the content of the book, there's something that I really would like to ask you because there's a lot of interest in USA. See, the US audience, particularly AMS audience, is always watching on TV the European model and the American model. Oh, that's the hurricane trajectory from the European model. This is from the American model. And if I may say so, although I hope my friends in the National Weather Service will not be upset, I think the general consensus is that European model is a bit more accurate. That's sort of what we hear. I have not done any verification. So I was just wondering if you can sort of tell us something about, because you, after UK Met Office, went to European Center. What is the secret sauce of the European Center? And what's happening in US? And what, you have any suggestions? So,
well,
yeah.
I mean, I wouldn't like to be perfectly honest, I haven't looked at the scores, recently. So I don't know, what the relative performance of, NCEP and ECMWF is. But it's certainly, most of the time I was at ECMWF, I mean, ECMWF was the clear kind of leader in the pack. And as you say, people, I mean, I used to get many times project managers from different agencies coming over to ECMWF, and they would ask that question, what's the secret of your success? And I would say, actually, it's quite simple. I mean, ECMWF is an international organization, and it can choose its scientists from, all of the European countries, and it's it's been a fairly prestigious organization to belong to. So, people want to come and spend some time at ECMWF, and of course the countries, pool. I mean, the budget for ECMWF comes from all the member states, so it's had a relatively good budget over the years, and that's enabled ECMWF to have big computers. So the secret really is, pooling resources. Now, the only thing I would say about the US is that, the agency system in the US does clearly create a kind of a series of, I would say, kind of quasi-independent organizations. So I don't, things are not quite as unified, and that may have hurt the US in the past. I don't know, but certainly the success of ECMWF has been the fact it's drawn on a very large international community and can basically take the best people, and it's had good resources to kind of develop its ideas.
Okay, obviously centers like European Center, NCEP in USA, and world over, they are trying to extend the limit of weather predictability. I'll just say they're trying to improve their forecast in a variety of ways. And I got a clear impression by reading your book that the whole concept of deterministic predictability limit, you have a difficulty with that. I think that maybe you can take a few minutes to explain what is your concern or difficulty or objection, and how. And you have implied in one of the chapters that the sensitivity to initial conditions for which we give credit to Lagrange was actually already pointed out by Poincaré. And so sensitivity to initial conditions is not something new in predictability, but there was something uniquely about Lagrange's work where he could actually explain to show that the structure of the tractor is very different, and it has implications. So I was just wondering if you want to just comment, because that has been in our language for a number of years. And I must say, when I was working on this, I used to write, the limit of deterministic predictability is, so please tell us Your view.
Well, okay. I mean, you've asked me at least two different things to talk about. So let me start with this notion of limit of predictability. I mean, maybe it's useful to tell you a little bit about my background. So I joined the Met Office. Actually, my early career was in stratospheric dynamics. I did work on sudden warmings, and I think the thing I'm most proud of is with Michael McIntyre, we discovered the existence of breaking Rossby waves in the stratosphere, and they play a really major role in the dynamics of the stratosphere. Actually, we now understand they play a role in the dynamics of the troposphere as well. And that was kind of deemed sufficiently, impressive that I got promoted to being what they call a group leader. The problem is that there were no vacancies in the stratospheric branch, so I had to move. This is the this is the British Civil Service at work. I had to move to a different area where there was a vacancy for a group leader, and there was one in the a branch they called synoptic climatology. And to be honest, I didn't really even know what synoptic climatology was. In fact, even to this day, I'm not entirely sure I know what it means. But anyway, that was the branch I was posted to. And it turned out that in that branch, what they were doing, the main thing was to do monthly forecasting, but not using, GCMs or dynamical models, but using what then was called statistical empirical models. We'd probably call them data-driven models, today, but the sort of thing that people may have heard of Jerome Namias. He was one of the real kind of pioneers in this field in the US. And there were two colleagues of mine, Chris Foll and David Parker, who, developed these statistical empirical models for the UK. And my job was to try to introduce, dynamical models, GCMs, NWP models. So the first thing that was sort of fairly obvious, I think, was that the forecasts we're producing from these models, dynamical models, would have to be probabilistic, because the basic statistical empirical models were producing probabilities of weather regimes over the UK. So somehow I had to develop a system where the output would be a probability of a weather regime. So it kind of became obvious the only way to do that was through some sort of ensemble approach. You run the model multiple times with, different initial conditions. And that would give you a probability, run it over 30 days. So we developed, this is with James Murphy, developed a kind of a real-time ensemble forecasting system, which I think was probably the first ensemble forecasting system in the world, real time anyway. It was moderately successful. It was successful in the sense that we were able to combine the results from the statistical models with the dynamical models, so that was all good. And it wasn't really considered very controversial. And then I moved to ECMWF. There was a vacancy in the predictability and diagnostic section, and I thought we should bring these ensemble ideas to the medium range. But that's when I got quite a lot of pushback, and the pushback was along the lines of what you said, that that Charney had sort of discovered there was this limit of predictability of whatever it is, 2 weeks, let's say. And people interpreted this result by saying that, for earlier lead times than 2 weeks, forecasts should be done deterministically, and only beyond the limit of deterministic predictability should they be done probabilistically. And I said, this is nonsense. The atmosphere is a nonlinear system. There is no fixed limit of predictability. It's like every day you can forecast to 2 weeks. Some days the atmosphere is going to be very predictable, and maybe you can predict longer than 2 weeks. And some days it's going to be very unpredictable. And to actually demonstrate that, I used Lorenz's model, the famous Lorenz 63 model. Now, normally, people think of, Lorentz 63 as showing that there is, eventually chaos means you lose predictability. But what you can do very easily is show how quickly you lose predictability depends on where you start on the attractor. There are some places on the attractor that are extremely stable, and where you can, for example, make a transition from one lobe to the other lobe, and there's very little growth of uncertainty. But conversely, there are other initial conditions where things, uncertainty can grow very rapidly. Anyway, I mean, this, I don't know, it persuaded some people, didn't persuade all my colleagues. But fortunately, nature kind of spoke, and there was a very famous storm in the UK in October 1987, where the weather forecasters on the television that would have got their forecast from the Met Office completely failed to predict what was literally the worst storm in 300 years, just the night before. And we showed, in hindsight, after the event, we showed that this corresponded exactly to one of these ultra unstable flows that you'd see in the Lorentz attractor. And that the only way you were going to have any kind of reliable prediction of these very unstable events is to run an ensemble. And then, you would give a probabilistic forecast of the storm. So I think it was, Lorentz's model definitely helped, but I think it was nature speaking that really, convinced most people. And we introduced the ensemble into the ECMWF operations in 1992. And
yeah, I was going to ask you about that actually.
Yeah,
because I was there at the European Center in December. There was a symposium in your honor to celebrate the 30-year anniversary of the ensemble.
Yeah.
What was not really clear to me till recently, that yes, there is always an institutional bias, institutional inertia. I remember even before you joined the European Center, Benson, who was the director of the center, wanted to introduce monthly and seasonal prediction effort, but he was getting a lot of pushback from the council. So it actually took quite an effort. Of course, right now, most of the people now accept this flow-dependent predictability concept, right? But what was not clear is that this is all implicit anyway in the Lorentz work. So, of course, I was going to ask you, how is this idea of ensembles can also be applied to other fields, and is it being applied, and how it can help society in fields other than just about weather forecasting?
Yeah. Just before I answer that question, just to clarify, there were two separate struggles going on at ECMWF at that time. One was the introduction of ensemble forecasting into the medium range, where, as I say, I think Charney's notion of a deterministic limit of predictability perhaps confused people, let's say, or in some ways it wasn't a helpful concept, I think, because people took it too literally. Now, the other struggle, which is quite separate, was trying to get ECMWF to develop seasonal forecasting systems. And I have to say, I got convinced that this is something ECMWF should do when I went to a meeting at the Royal Society where Mark Kane presented results from the Kane-Zibiak model and forecast the, I think it was the 86-87 El Nino. And this is an area where the US was massively in the lead. All sorts of people, Ants Liebner was doing ocean analysis. There was a great body of theory in ENSO, Mark and Steve and George Philander and lots of other people. And then Ushukla had, clearly shown how a knowledge of the lower boundary conditions would, particularly in the tropics, would be broadcast to the rest of the atmosphere. So actually, in the US, that was a case where the US was very strongly in the lead. And I just argued to people like Leonard and Dave Burridge that we should get on board this thing, because it's scientifically sound, and it's within the remit of ECMWF, because we're dealing with an initial value problem, and the benefits, could be fantastic. But again, some of the member states weren't happy. They felt it was mission creep and all that sort of thing. So it took quite a while to get the formal endorsement from the council to work on this. But we did eventually. And, we're in a happy position today where both ensembles and seasonal forecasting is done operationally at ECMWF.
I mean, it's quite interesting that in spite of the original medium range being in the title, it was a challenge to go beyond. But I was sort of quite taken aback that even for ensembles there was such a pushback. And but now it's common. US started showing multiple trajectories quite in the beginning on the hurricane track. And
so just to answer your second question, which was about how does it work in other fields, and that was something I tried to look at in my book. For example, we had this big financial meltdown in 2008, big financial crash. It affected the world's economy. How predictable was that? Was that a bit, the question is that like the storm, the 1987 storm that ravaged southern England, where it was, not predicted because it was extremely unpredictable? Or actually, was it very predictable? So I started to ask economics colleagues that I knew and wrote to other ones, what's the status of this? And do you have anything like an ensemble forecasting system? And the answer I got back was no. We're just not sufficiently advanced in economic model to even sort of contemplate such things. But actually, as I started to write the book, write that chapter in a rather sort of negative way, but I put out sufficiently many feelers that I got a few emails from economists. There was one in Austria in particular, who actually had started to work on ensemble prediction. So I kind of finished the chapter with some hopeful remarks that I think this is an area which could be a growth area for economics. But a key question is, and I don't think this is a good time to go into it, but what are economic models? And it turns out there are different types of economic models, and some are just not suited to ensemble prediction. There's a type of model called an agent-based model, which is more suitable to ensemble prediction. And in fact, agent-based models actually have been used for COVID prediction. And this is an area where actually ensemble techniques have kind of flourished during the COVID outbreaks. And particularly in the US, where, multiple kind of COVID prediction models have been developed. It's been realized that pooling the models together in a kind of multi-model ensemble is actually the best way of synthesizing all that information. And there's been quite an active growth area, I would say, in ensemble epidemiological modeling, which was spurred on by COVID. So that part of I wrote a chapter on that as well, and that's I would say I sort of feel that's in a better state than some of the basic economic modeling.
Oh well, you can be very proud that it is in such good state that I have watched congressional proceedings sometimes on TV, and the congressmen and senators show the consequences of their policies, the deficit, and they show ensembles. I'm just amazed. I don't know, I'm sure the staffers made it for them, but they actually show a cloud of thin curves, and then they show, anyway, so I think it is there now, it is within. By the way, you have mentioned a couple of times this, just coming back to this butterfly effect and a 2-week limit and Charlie's name. I really feel like I should just take a minute to help also the audience, because see, I talked to both of them. Of course, I was the privilege to be the student, Charlie and Lorenz. What really happened was that once the Lorentz wrote this paper. First, it was not known to many people. Of course, Charney knew it. But Charney was proposing this global weather experiment. And the global experiment, because John Kennedy had announced it and now the news was filled with, oh, we're going to have 2-week forecast. Okay, because 10 days to 2 weeks. They didn't say 2 weeks, literally 2 weeks came later. So then he got very worried, Charney, once he saw Lorentz's paper. And he talked to Link. Then he immediately decided to calculate the error growth rate. But there were only 3 models those days, Princeton model, GFEL, and Leith and Yale-Mills. They all calculated the doubling time of a small error. And only one of them models gave reasonable doubling time of 5 days. And Charney, I mean, he really had to rescue this intellectual objection to the experiment. He chose that one. And he says the doubling time of one of the good models is 5 days. And therefore, we have come to the conclusion that the limit of prediction deterministic behavior is 2 weeks. That's the origin of the 2 weeks. Okay, that sentence in Charney's report, Lorentz, you can go through all his papers, never has written 2 weeks anywhere. He just said there is a limit. He says growth rate, doubling time, saturation value. So I think that, but it does lead me to a question. And I'm going to put you on the spot. What do you think is the limit of weather prediction? And when do you think we'll know it?
Well, as I say, I don't think, you have to sort of acknowledge it's sort of not a terribly well posed question, I think, is I had to briefly answer it. I mean, it's clearly a statistical average. And it does depend on, are you talking about pure atmospheric predictability? Are you allowed to bring in the slowly varying boundary conditions from the oceans and the land surface and so on? Because clearly they impart their own predictability. So I just feel it's not a terribly in some ways, it's not a terribly well-posed problem. The only thing, I do have a chapter talking about, Lorentz's famous 1969 paper, which is less well known and understood, which raises the really interesting, I think, theoretically interesting idea that, you see, the thing about Lorentz 63, you can predict as far ahead as you like, providing the initial uncertainty is small enough. Yeah. So if you want to predict, 1,000 years ahead, I'll tell you how accurately you need to know the initial conditions. It will be, of course, ludicrously accurate, but nevertheless, you can make that point. But Lorentz 69 is the one, in a way, Lorentz 69 is the origin of the butterfly effect, the phrase, the butterfly effect. And the idea there is that actually there may be an intrinsic limit that you just can't exceed. But, this is in a very idealized framework where there is no kind of signal from the boundary conditions or anything like that. It's just a pure atmospheric predictability. So pure atmospheric predictability, on average, it may, and I'm talking about instantaneous predictability as well, so you're not time averaging or anything, then yeah, I mean, maybe 2 weeks is about right. But, there are so many things which add to that, particularly from the boundary conditions and so on, that
So I would like to move on from weather to sort of longer time scales, because see, this this idea of ensembles and the contributions to modeling in many fields, and this whole idea has served the weather prediction community and weather prediction field very well. How will these ideas can be extended to the climate predictability, climate prediction, climate adaptation? What I know you have been thinking about it, and you have made some hints in the book. Can you elaborate on that? Its extension to climate.
Well, let me just preface. I'll answer that question, but let me just say one thing. When I was at ECMWF, obviously, I used to argue for computing resources to do ensembles, and I I would say, it just makes no sense to develop a high resolution deterministic model if you've got no idea how, reliable your deterministic prediction is. So we had the ensemble, but, for many years, the ensemble would run at a lower resolution than the deterministic forecast. And it was always a kind of frustration to me that, the ensemble had to run at a lower resolution, because I recognize that resolution, is important. A resolution, the higher the resolution of your model, the more you are representing the laws of physics accurately. And one of the wonderful things that will happen fairly soon now, I think, is that ECMWF is switching to a single resolution, 9 kilometers, where the ensemble and the deterministic forecast, which basically means there'll only be an ensemble, is being run at 9 kilometers. Now, so, resolution is, my experience at ECMWF has been that increasing resolution has been super important. It's one of the main things that has helped the skill of the models go up. So once you have an ensemble system, then you should strive for as high a resolution as possible. Okay, now when we come to climate, climate models have been great in warning the world about the dangers of climate change, of global warming, and climate change more generally. But we still struggle with our kind of conventional climate models to simulate, particularly on the regional scales, the weather patterns that give rise to weather, whether it's drought or flood or storms or whatever. And hence we struggle to simulate reliably the effects of climate change on these weather events. Now, that's a problem, I think, if you're trying to decide how to adapt to climate change. Are you adapting to hotter, drier weather or to kind of wetter, stormier weather? If your models aren't reliably simulating the weather, then you don't know. So I think there is a, like weather forecasting, I think there's a pretty strong reason to really try to get as high resolution as possible. And a group of us believe, we can't prove it yet, but that if we could get to resolutions where we're no longer dependent on some of the really important parameterizations like deep convection, like orographic gravity wave drag, which I used to work on years ago, like ocean mesoscale mixing, we do a much better job at simulating climate. But, running a climate model at, say, 1 or 2 or something kilometers, 3 kilometers, is fantastically computationally challenging. So the idea is, well, maybe like, ECMWF, I said earlier, we benefited from pooling resources to produce, certainly for most of its time, the most skillful medium range system in the world. Maybe we could do something similar for climate change, pool resources from different countries. It wouldn't just be Europe necessarily, it could be countries all over the world, to produce kilometer scale models for climate. And I just think, climate is becoming so important these days, climate change. It's not, we're now talking about loss and damage caused by climate change, adaptation to climate change, whether we need to start thinking about solar radiation management, geoengineering. We've got to have, reliable, these are kind of, big issues now, for society. So we've got to strive, I think, to have better climate models, more accurate climate models, where the biases are smaller and where we're confident that they can simulate the sorts of extreme events that we've seen in the last few years in the real world. So I'm a great believer in, ECMWF is a great experience. Obviously in my earlier work in physics, CERN was a great role model, again, another international organization which did things that individual countries couldn't do. So I'm just wondering, is climate modeling something which would also benefit from a more international approach? And well, you and I think both agree that it should, and we had a big summit at ECMWF some years ago. We're going to follow this up with another summit in Berlin later this year, and maybe things might start to happen.
Good. By the way, there is a question from Ed in the question answer about what we are doing now. So I just wanted to let Ed know that we'll come to that after finishing the book about what Dr. Palmer is doing now. And also, any of you have any questions, you can type in the question. We'll take them after about 5-6 minutes when we come to that. I have actually a question about noise. I'll tell you. So I don't mean any disrespect, but there was a movie in USA. The title was "Greed is Good." Greed is good. And greed is good. Okay. And let me just tell you the reason I'm giving this example is that. So one of the impressions I got by turning through different chapters here and there in your book is noise is good. Okay. And I said, okay, obviously, no, it's not a good comparison, but you know where I'm going, right? Our general impression is, in climate research, we're trying to get rid of noise. We have techniques to filter noise. We have got numerical techniques to get rid of noise and try to get. So this is quite an interesting, I really wanted you to explain that to the audience, how you see because you claim that noise may be even important for human brain development, let's say. And so
yeah, well, we're running out of time, so let me just go very quickly. It was clear in the early days of the ensemble that we needed to represent model uncertainty as well as initial uncertainty, and adding noise into the model was actually a good way to do that, what we would call multiplicative noise. So when the parameterization tendency was large, this noise term would be large. And that really seemed to, that made an enormous difference to the reliability of the ensemble particularly in the tropics. But then I kind of got interested in whether this noise would actually help reduce the systematic errors in the model. And the idea there is that, in a nonlinear system, as opposed to a linear system, noise can do things which could be beneficial to the system. And there are many nonlinear systems where that's the case. I discuss a few of these in the book. People familiar with paleoclimate might be aware of the notion of stochastic resonance. Adding noise can maybe help us understand why the Earth reacts so sensitively to the Milankovitch cycle, because noise can amplify that small forcing. And then I got interested in, if noise is so important in climate models, why are we insisting that our computers are bit reproducible, particularly if that puts an energy overhead on running the computer? Maybe we should make our chips noisy. We could run them at lower energy and benefit from the noise rather than anything else. So that got a very kind of skeptical reaction when I mentioned this. So then I started thinking, are there physical systems in the real world where noise is actually a constructive resource? And the more I got looking at the brain and how the brain works, and I talked to a large number of neuroscientists about this. The brain is clearly a very noisy place. We do almost the same amount of data processing as an exascale computer, but with 6 orders of magnitude less energy. It's extraordinary. But there's a penalty for running, 80 billion neurons on 20 watts of power, which is that the brain is susceptible to noise. But it may be that that's not actually a bad thing. And maybe, some of our creativity arises from being susceptible to noise. So, you know, so that was, I mean, that's still a little bit speculative, but that, you know, gives an example of a physical system where noise actually can be a constructive resource. So I kind of got interested in noise more generally. I mean, it started off as a way to just to get the spread of the ensemble more accurate, but it's quite an interesting field, I would say.
Very good, Aloy. So I think so happens that what I was trying to ask you in the end is pretty similar to what one of the audience members at Neblock is asking, because, you know, of course, you started with quantum physics, then you move on to atmospheric dynamics and chaos. And what I got the impression is that now you are trying to come back to the quantum physics. However, you want to address how it can be, the ideas can be improved by using chaos. Can you explain that, what it is that you are doing, and in a few minutes?
Well, I mean, the holy grail in theoretical physics when I was a student is really hasn't moved on very much, which is how do you unify gravity and quantum mechanics into a single theory, what people sometimes call quantum gravity. But there's a real problem with this, which is that Einstein's theory of gravity is deterministic, it's nonlinear, it obeys, you know, certain laws of causality. Whereas quantum mechanics seems to be completely the opposite. It seems to be quite linear. It doesn't seem to be deterministic, and it seems to kind of violate this notion of causality. So it has this property of what's sometimes called spooky action at a distance. And in fact, this year's Nobel Prize in Physics was for experiments which seem to suggest that that quantum physics has this spooky action at a distance. So my view is that we will never unify gravity and quantum mechanics unless we can really, you know, unless we can actually show that there is a deterministic causal underpinning to quantum mechanics. So I've actually been quite interested in using some of the, if you like, geometric ideas behind Lorentz's attractor, the fact it's a kind of a fractal in state space, to look more closely at some of these quantum theorems. There's a very famous one called Bell's theorem, which I won't have time to talk about, which most physicists think proves that there is spooky action at a distance in quantum mechanics. But my view is that if one takes some of the ideas behind the geometry of chaotic attractors, one can actually show that that is not a robust conclusion, and that there actually may be, like Einstein believed, there may be a deterministic underpinning to quantum mechanics which satisfies all the normal kind of relativistic laws of causality. So that's my you know, I'm kind of returning back to my days of my PhD to some extent, but making use of all the stuff I've learned as a meteorologist, and in particular all the stuff that Ed Lorentz has you know, has given us through his career.
Okay, we have another question from Tim, another Tim Del Sol. I enjoyed listening to your perspective about using dynamical instability theory, high resolution models, and ensemble methods to study predictability. Are there other lesser known tools for studying predictability that you believe are underutilized?
Well, I think the really big issue today is AI. You know, and there are now some groups in the world that claim that AI can do as well as physics-based models. And I'm personally skeptical that that's the case. But I think we can't ignore AI. And actually, I think, again, we have to you know, try to use it to our advantage. And in particular, I mean, one thing which, I mean, this is relevant perhaps to this notion of climate modeling at kilometer scale, because people say sometimes to me, oh, well, if you have a kilometer scale model, you'll only be able to make sort of 10-member ensembles. And we know that, we need large ensemble sizes. Well, one possibility is that we could use the 10 members as a kind of skeleton for an AI system, which basically fills in the distribution in a kind of in a physically sensible way. And that seems to me one, application of AI where, it's not one or the other. It's not physics-based models or AI-based models, but how do we make use of both of them in an optimal way? I think this is a big challenge for our field, both in weather prediction and climate prediction going forward. We've got to kind of embrace AI technology, but we mustn't be beguiled by some of the hype. AI is great for interpolating, but it's less good for extrapolating. So we still need our physics-based models to do the extrapolating, but maybe AI can help with some of the interpolation problems, for example, in phase space.
Actually, I have a question for Gideon, who is the AMS organizer, because I don't understand this technology, Gideon. Can participants actually ask questions? Because I just want to know whether Tim had a follow-up question. Can he ask, or is it has to be only by typing?
Yeah, generally we're just looking at the Q&A for questions that are submitted to the guests.
Right. In the Tim, the one part that when you were talking about the different modeling groups combining their resources and so on, you have also made this proposal for chips being less precise. So that's another sort of counterintuitive argument, and maybe it has to do with your sort of general sort of notion about the role of noise. Can you just explain that?
Well, I mean, again, that started with having kind of worked with stochastic parameterization, noisy models and things. I was sort of reflecting on that one day, thinking, well, why if our models are noisy, do we we run everything with 64-bit arithmetic? And well, basically, I mean, I had at the time one of my postdocs, Peter Dubin, who's now actually got a senior position at ECMWF, who essentially recoded the ECMWF IFS model with 32 bits. And I mean, that actually took some time because it blew up all the time, but he realized that it wasn't blowing up for any fundamental physical reason, but that the coding wasn't that good. And if he kind of recoded the order of operations and things, he found that actually it worked very well. And a couple of years ago, ECMWF actually, as a result of this work, moved to 32 bits. And the amount of time that they saved, they used to increase the vertical resolution of the model, which made the model more skillful. And I often think this is one of the few examples of a cycle change, which has significantly improved the skill of the model, but actually with less, using less computational resource. So I used to argue, the sort of aphorism, if that's the right word, is more accuracy with less precision, which means you reinvest the computer time that you've saved by reducing precision to do something that's a bit more useful. Now, the interesting question is whether we can go down further. And of course, a lot of AI stuff is done at 16 bits or even less than 16 bits. And what we found, and we've got a paper in the QJ actually looking at, I think it's almost out, looking at climate change integrations with 64, 32, and 16-bit numerics. And the short answer is, if you introduce what's called stochastic rounding, so you don't always round your numbers to the nearest representable integer, but you round them either up or down with a probability, with a sort of stochastic generator, then actually you can do as well with 16-bit arithmetic as you can with 32 or 64. And again, I think this is important for these high resolution models, because we're going to need every every flop, if you like, we can get hold of, because we're right at the limit of being able to run multi-decadal forecasts with kilometer scale models. We've got to really get the models as computationally efficient as we can. And of course, the other great thing about 16 bits is, you start to make really big use of use GPU technology, which can be, very fast chips and things. So it's an area which my group works on. I don't actively work on it myself, but I just feel it's an important area. We've got to really think hard. And this is another area, by the way, where AI can help, I think, make the parameterizations and the Earth system modules much, much more computationally efficient than they currently are.
Okay, last question. American Meteorological Society likes to, encourage education of young people and interest. What will be your message to a young scientist, or what are the exciting problems?
Well, I'd like to address a message to a sort of a young version of me, which is to say, a lot of people who become meteorologists were fascinated by weather as children, which is great, of course. But I would like, people who work, on high energy physics or cosmology or number theory, or areas which don't seem to have anything to do with meteorology. They probably have developed a passion to do that in their younger days, but they need to be given the opportunity, once they've got that out of their system, after their PhDs, maybe after a couple of years of postdoc, we should develop the means to allow people like that to move fields, because it's that, it's often, when you're in your 20s or something, you develop a kind of a social conscience. You've done your thing in cosmology or number theory, but now you want to help society, and we've got to find ways of allowing people to kind of move fields more fluidly. So my message to people, do whatever you feel passionate about, and don't feel that typecasts you for the rest of your life. I hope in future society we don't think of science in a very siloized way. New ideas in a particular field typically don't come out of the ether. They just come from somebody moving from a different field into our field.
Leaders.
In fact, in my book, I talk about Chuck Leith. I mean, Chuck Leith developed some of the first Monte Carlo forecasts, and he did that because he started to work on the hydrogen bomb after the war, and the Monte Carlo technique was developed by Ulam and Teller and people like that to try to solve the simulation for the bomb. So the whole ensemble Monte Carlo stuff actually came out of bomb technology. And of course, Chuck, Leith had moved from that field into climate, so he brought those ideas with him. We need to benefit much more from this, movement of fields, and we're too siloized at the moment.
Yeah, well, by the way, you mentioned Chuck Leith. I was just amused to read just only recently. He's the first one single-handedly developed a GCM. He was visiting Norway. He was the first one, even before GFDR, single-handedly. All these models are. Anyway, I think we have run out of time, and I really would like to thank you. Gideon, you have any last comments to make? Because I think that so far as I have addressed all the questions that came into the question and answer, and I say we have hardly a few seconds left. So it's all yours now, Gideon. Thank you very much.
All righty. Well, hey, thank you very much, Drs. Palmer and Shukla. That was fantastic. Very informative. And now I have another book on my book list to dive into. So thank you for that. Audience, we will make this video available to Weatherband members at amsweatherband.org and at ametsoc.org. So yeah, thank you all for joining us today. Thank you so much for all your work in helping to put this together, doctors. And audience, we will see you at our next webinar. Have a good day, everybody.
Thank you, Tim. Thank you.
Thank you. Thanks,
Thank
Shifter.
you. Take care.
Bye now.